At Northrop Grumman, innovation isn't just an idea. It's a way of life. The value of performance. Northrop Grumman.
Thank you and good morning. I do apologize for not being Robert Lang, and really I would have liked to hear Robert myself. However, I do have something to tell you about today. It's about games that people don't play. Now, you might be asking yourself the question, what is a game for if you're not supposed to play a game? And it's a pretty reasonable question. And what these games are for is they function as mathematical puzzles. Now, the fact is that mathematicians and computer scientists use games to understand phenomena. They use games to understand algorithms. They often deal with an adversary who they imagine is going to make a problem as difficult as possible, and then they try to figure out a way to solve it anyway. This is what the promised adversary looks like. I made him myself. And we'll get to see him in action in a couple of games. Okay, so I'd like to start with a couple of games where the idea is just to guess whether one of two numbers is the smaller number or the larger number. I mean, what could be easier? Here's how the game works. I'm going to write down two different numbers on two pieces of paper. And those numbers they're going to be whole numbers, but they could be anything. They could be anything from minus infinity to plus infinity. I'm just going to write those two numbers down, and I'm going to put one of them in my left fist and one of them in my right fist. And then you get to pick one of my fists and open it and look at the number inside. So here's an example. You've chosen the hand at the left there, and you've opened it up and found the number minus 617 in it. And now with maybe $1 at stake, you'd like to guess, is that the larger of the two numbers that I wrote down, or is that the smaller of the two numbers? So what do you guys think? Yeah, smaller, sure. I mean, there's a lot of room above minus 617. Of course, you could argue that there's also a lot of room below minus 617. Is there any way to know? Okay, so this is a game. You've got to guess. You know, you don't know anything about my psychology, and the psychology of the adversary is something you can't know. Maybe I always choose two numbers, one of which is in the minus 600s and one of which is in the minus 700s. Who knows? How can you play this game? How can you get more than a 50-50 guess at this game? Amazingly, there is a way you can play this game that guarantees that you will win it with probability better than 50%. Okay? And this is actually a kind of a sophisticated solution. It's a precursor to seeing what computer scientists often use. It's called a randomized algorithm, and here's how it works. Okay? First of all, you as the guesser have to decide on some way to acquire a random number. Okay? You need to, and there are lots of ways you could do it. I mean, you could flip a coin to decide whether your number is positive or negative, and then maybe you could flip a coin and many times until you finally get a head on the coin, and count the number of flips you made, and that would be your number. The important thing about this method is it has to be possible for you to get any particular number. Not necessarily likely, but it has to be possible that your random number could be minus 816, or it could be plus a billion, or it could be plus 4, could be 0, could be anything. So what are we going to do with this random number? Well, we're going to add a half to it, and then we're going to use that number as a random threshold. Okay? That number becomes our magic number. When we open a random hand and look at the number inside, we compare that number with our magic number and use it to decide whether to guess that this number is the smaller number or the larger number, right? So for example, suppose that your random number was 15, okay? And you add a half, so your random threshold becomes 15 and a half. Now you look at my number, it's minus 617. That's lower than 15 and a half, so you guess that it's the smaller number. If the number had been 21, you would have guessed that it's the larger number. If the number had been 14 or 15, it was below the threshold, so you would have guessed it was the smaller number. So that's the algorithm. And the question is, why should this work? Why does this give you an advantage in the game? Well, let's think about it. The answer is this. Suppose that my two numbers are both above this choice. Okay? Then whichever number I pick, I'll guess that it's the larger number, and I'll be right half the time. Another possibility is that my two numbers are below the guess number. And again, if I pick, I'll always be guessing that the number is the lower number, and I'll be right half the time. So the key is that sometimes this random number will be between my two numbers. And in those cases, you'll win no matter what. No matter which number you pick, you're going to guess correctly. And that extra edge is what gives you the edge in this game. Okay, everybody got it? All right. Now, interesting things happen sometimes when you change the rules of a game slightly. So I'd like to change the rules of this game a little bit in the following way. Okay. So first of all, instead of picking the two numbers myself, I'm going to get handed those two numbers by Tyche, the goddess of chance. And those two numbers are going to be random, real numbers between 0 and 1. Who knows what a real number is? All right? A real number is anything that can lie between two numbers. It could be a half or a quarter, or it could be an irrational number like pi over 4. Okay? Some number, random number between 0 and 1. And I get two of these numbers, and the other difference is I get to decide which one you see. You don't get to pick my two fists. I get to decide which one you see. It turns out, in this game, sounds maybe better for you, but in this game you can't do better than 50%. And in fact, I have a strategy that I can use in this game which will, even if you know that I'm using it, won't help you. Won't help you play the game. And what's the strategy? So I picked the number to show you that's closer to a half. So why should that work? I don't know. So imagine the number is 0.38, right? And I'm telling you flat out that that's the number which is closer to a half of the two numbers. Well, what do you know about the other number? It's either between 0 and 0.38, or it's on the other side. It's between 0.62 and 1, and those intervals are the same size. So it's automatically 50-50 whether that 0.38 is the smaller number or the larger number, and nothing you can do can change it. Okay. You ready to switch to a more delectable subject? Okay. I'd like to tell you about a game called Chomp. All right, now it's not lunchtime yet, and we're going to talk about dessert, so just hold off. Okay, and this game is played on a chocolate bar, and it's a chocolate bar which has been scored into squares. And in this case, it's a 6x4 rectangle, but in this game it could be any number by any other number. The important thing is it's a bunch of squares in a rectangle, and there's more than one square. Otherwise the game is not very interesting. Here are the rules of the game. So the first player picks a square. So there's a square. And now she bites off that square and everything that's north and east of it. Everything to the upper right. Okay? She's bitten off that piece. That's her turn. Now it's Bob's turn. Bob picks a square. Maybe he picks that one. And then he bites off that square and everything north and east of it, and that leaves this. Okay? If the object of this game were to eat as much chocolate as possible, it would not be that interesting a game, right? Because what would Alice do? Alice would start with the square in the lower left and simply eat the entire chocolate bar, and that would be the end of the game. Okay, so here's what makes it interesting. Here's the catch. The lower left-hand square of the chocolate bar is poison. Okay? So you don't want to be eating that square, and all you have to do to win the game is make sure that it's your opponent who has to eat that square. Okay? So we play for high stakes here. Okay? So there we go. So we want to eat this chocolate bar carefully and make sure that we're not the one who gets stuck with the square in the lower left-hand corner. Everybody clear? Okay. Here is the sad fact about this game that I have to tell you. We actually know who wins this game, but we don't know how. Okay? This is a very strange state of affairs. The fact is that we know that the first player, no matter what the size of the chocolate bar is, the first player can win this game, and we don't know how she does it. How can this be? Well, let me show you the proof. The fact is, this is a finite game, and someone can win this game if it's played right? You know that, for example, tic-tac-toe ends in a draw if it's played correctly. Some games, we know now from computer searching that checkers ends in a win for the first player if everything is played exactly correctly. So in this game, either the first player can win it or the second player can win it. So let's assume for a moment that it's the second player, Bob, who can win this game. So what happens? We ask the following question. If Bob can win this game, what does he do when Alice takes the upper right-hand corner for her first move? So apparently he has some winning move in this position. What is it? Well, there's the square gone, and let's suppose that that's his winning move. Right? So he bites that off, and now it's Alice's turn. Now, supposedly, this position is a winning position for Bob. Right? No matter what Alice does after this, Alice is going to get stuck with the poison square. But there's something wrong about this, because if this is a winning position, Alice could have done it in her first move instead of taking the upper right-hand square. So what have you just seen? You've seen a proof by contradiction. We've assumed that Bob has a winning strategy in this game, and we've proved that that can't be. If he had a winning strategy, Alice could steal it. So Bob can't have a winning strategy, and we conclude that it's Alice that has a winning strategy. But this argument doesn't tell us what that winning strategy is. So we actually know how Alice can win the game if the bar is only 3 squares deep. But beyond that, nobody knows. Maybe you guys can figure it out. Let me show you one more curious game. This is a card game. And in this card game, I take a deck, shuffle it well, and turn over one card at a time, and you get to stop me whenever you want and bet that the next card is red. And you have to stop me at some point. You could wait for the last card, and you'll know whether the last card is red or not if you've counted the cards. But you won't be able to do anything about it because you're not allowed to bet that the card is black. You can only bet that the card is red. Okay? So the question is, what's the right strategy for this game? And there's a marvelous proof that, amazingly, there is nothing you can do in this game. There is no strategy better than 50-50, and there is also no strategy that's worse than 50-50. This is the reasoning. We imagine a variation of the game where instead of turning over the next card, you turn over the last card. That card has the same probability of being red as any other card in the deck. Any strategy you have for the first game is going to work equally well for the second game. But you win the second game exactly if the bottom card is red. There's nothing you can do about it. That concludes my games for today. I hope you guys have got some food for thought here and can invent your own variations for these games. Thank you very much.